In this lesson, we are going to introduce the idea of a substitution rule, so better known as a U substitution. And so this form of integration is going to be needed if you would have had to have used a chain rule while you were doing the derivative. So remember that these are derivatives, and we are going to undo them to find out what their original functions were. And this, having this quantity inside raised to a power, if we would have done the derivative, would have had a chain rule associated with it. And so part of it also is recognizing that if you have a chain rule, you're also going to be doing the derivative of the inside, and the derivative of x squared is a 2x. So there's little pieces that I'm looking for, like that as a chain rule feel, which means to undo it, we have to use a U substitution. So it's going to be recognizing the pieces. And so the first thing that I'm going to do is I'm going to rewrite this. So I'm going to take this x squared plus 1 to the 4th. I'm going to clump the 2x connected to the dx. It's all multiplication, so I can kind of rearrange it wherever I want. And what I want to do is to figure out which one of these should be the u, and then I'm going to take the derivative of it. And so what I'm looking for is that this is the derivative of this, right? 2x is the derivative of x squared. And the coefficient doesn't have to match perfect. It's really the powers I'm looking for. I do the derivative of an x squared, I'm going to get an x. So that tells me that I should take this x squared plus 1 and do the derivative of it. So if I do the derivative of this, this becomes 2x dx, and wonderfully, that matches this. So we're going to start to do some substitution. This is the U substitution idea, that this piece that we're going to replace it with U. So we're really looking to do the antiderivative of U to the 4th, and then 2x dx I can replace with du. So the whole idea behind this is to turning it into something that's complex into something that's a lot nicer to do the antiderivative. And so I do the antiderivative of this. I'm going to increase the power by 1 and then divide by that power. And then my last piece to this, I'm going to add a plus c because we're not doing a definite integral, we're doing an indefinite integral. And so we're truly finding what the original function was. And so I have a 1/5. And now instead of u to the 5th, I'm going to pull this back in. Have x squared plus 1 to the 5th plus c. And so I can also do this derivative and see if I would get it back to this. So if I would do the derivative, the 5 would come down and cancel. This would become a 4. And then it would be chain rule would be applied. So times the derivative of the inside, which is 2x. And then the derivative of a constant would go away. Right? So let's do that on one more. So exponentials and logs and trig values are always technically chain rules. And so this piece on the top here, I'm going to let that be my u. All right. And so if I take the derivative of that, I'm going to get a 10 dx. And so I don't have a 10 on here, like I had this perfect 2x dx matching. So what I'm going to do then is pull that 10 over. So I'm going to divide it over to the other side. And so the best that I can do is that dx I'm going to be replacing with 1/10 du. And that exponent I'm going to be replacing with a u to make this exponential a little easier to work with. So since it's a constant, I'll put the constant in the front so I don't have to try to complicate my antiderivative. And then it's an e to the 10x is now going to be subbed in with a u, and then du. And that is a far simpler type of a problem to do. So if you remember that in general, when you do a derivative, the derivative is just itself. So if I'm starting with an EU when I'm doing the antiderivative, it's just going to be itself. So it's 1/10 e to the u plus c, and then I'll pull the u back in. So 1/10 e to the 10x plus c. All right, so that was a couple examples. We'll do some more videos that do different situations and kind of more practice on them.